Cool. I guess let me get started. Hi everyone, my name is Chenglei. I'm a rising third year PhD at Stanford NLP, and um, this talk is designed to be roughly about 50 minutes, and hopefully we'll have some time in the end for more open-ended discussion. If you have clarification questions, you can just ask during the talk itself. All right. So the title of this talk is The Art of Evaluating Research Ideas. I want to begin by talking about why do we even care about evaluating ideas. I think as human researchers, we all care about the task of evaluating ideas because executing an idea can be quite expensive. It could mean a couple of months of hard work in the lab. It could mean a couple of $1 million if we're talking about pursuing experiments. So we probably want to find a way to identify and prioritize the best ideas that we can think of. And another motivation for figuring out how to evaluate research ideas is also there have been this vision of building end-to-end research agents that can automate scientific discovery. And really, the first and most fundamental step of this whole pipeline is for the AI scientists to generate effective research ideas. And so we probably need to find a way to evaluate how well these AI scientists can generate ideas as a first step. So with that as a motivation, I will lay out some dimensions that we should consider when talking about evaluating research ideas. The first dimension we could consider is, are we using LLMs to do the evaluation, or are we having human experts doing the evaluation? The second dimension we could think of is, are we evaluating just the ideas themselves, or are we actually executing the idea into actual products and then evaluate the executed products? A third dimension we can think of is, are we evaluating LLM ideas, or are we evaluating human ideas? Now I'll discuss some existing paradigms and see how they situate in this 3D space. So first of all, we all know about the whole peer review system where human researchers brainstorm their ideas, they execute their ideas into products, and they submit them to peer review venues for experts to review their work. On the opposite end of this, there has been a bunch of research work on having LLMs generate research ideas, and they would ask some sort of LLM judge to evaluate research ideas. And this is a research topic on its own. Some folks are not just satisfied with having LLMs judges evaluate the ideas themselves. They want to build a full pipeline. So a bunch of folks have built things like AI scientists where they will have the LLMs generate ideas and then build execution agents to execute the ideas into full products, and then let LLM just evaluate how good the actual products are. And soon after that, these folks are not satisfied with just asking LLM just to do the evaluation anymore. So some of them actually decided to submit the executed products into workshops and conferences, and some of them actually got accepted and accurate workshops and even ACL. So these are some existing paradigms and how they sit in this 3D coordinate space. The goal for this talk is I want to describe a set of experiments that we have done in the past 2 years that will hopefully cover the whole space of the 3 different dimensions in a setup that is as controlled as possible. And this will allow us to answer some interesting research questions. And I will focus on specifically the following 3 questions. First of all, can LLMs generate better ideas than humans? Second of all, how does evaluating ideas differ from evaluating the executed projects? And lastly, how well can LLMs automate this whole evaluation process? So let's go back to this 3D space. There are 3 dimensions we could think of to make things easier. Let's just forget about the first dimension on using judge for a bit. This can reduce the 3D space into this 2D space. So let's consider, let's say we're comparing AI ideas versus human ideas, and we could either evaluate the ideas or evaluate the executed products. And I'll start by thinking about this comparison of AI and human ideas when we just evaluate the ideas themselves, and I will describe our first study in this particular setup. So first of all, let's collect some human ideas. We have a set of 7 different NLP research topics, including bias coding safety, multilingual factuality, mass and uncertainty. And we have recruited a bunch of human researchers to select their favorite idea, select their favorite topic out of this list and write ideas for us. And you can see most of these people who contributed ideas to us are current PhD students. And in this table at the bottom, I'm showing their Google Scholar profiles. So you can see when they join the study, they have an average of 12 papers on their profile with an average of 477 citations. So this means they have substantial research background when they contributed their research ideas to us. So this is how we gathered a total of 49 research ideas from human experts. And we also built an LM agent based on cloud. This agent is very simple, where we just give it a research topic to the agent, or retrieve some relevant papers, generate tons of ideas, automatically rank them, and then output the best ideas. So we generate a total of 49 ideas to match the exact same distribution of our human ideas. Now, to give you a sense of what these ideas look like, here are two concrete examples of human ideas and AI ideas. So you can see that each idea would consist of several components. I have a problem statement, I have a motivation, I have a proposed method section, and I have a detailed step-by-step experiment plan. If you look at the right side, the experiment plan would consider various steps, including what data sets you should use, what baselines you should compare with, how to implement every single step of your proposed method, what metrics to use for evaluation, what analysis and evaluation slides you could run, etc., etc. So we make sure every single idea is very detailed, to the extent that we can actually give these ideas to some human researchers to work on in a later stage. So this is how we created the human ideas and AI ideas. Once we have gathered all the human ideas and AI ideas, we pass all these ideas to a set of expert reviewers to do a round of blind review on these ideas. Again, we are recruiting really awesome people as the reviewers here. You can see on the left, these people are mostly PhD students, some are even postdocs, and they have an average of 15 papers when they did the reviewing. So substantial research background again, and they come from a bunch of amazing places around the world. So next, I will show you the review results of this first study. And remember, the goal here is to compare human ideas versus AI ideas. And here I'm showing results of aggregating all the review scores for human and AI ideas. The yellow bars represent the human ideas, blue bars represent AI ideas. So you can see that on most metrics, including novelty, excitement, effectiveness, and overall score, the blue bars are higher than the yellow bars, meaning AI ideas are actually scoring better than human ideas. The only exception here is the middle one, where AI is actually slightly lower than humans on feasibility. If you prefer to look at the numbers, here are the detailed breakdown of all the results. The numbers here are computed in a slightly different way, where we treat each idea as an independent data point rather than treating each review as an independent data point. So the sample size is exactly 49 here, because we have 49 ideas for human condition and AI condition. But really, the overall trend is the same. If you look at the numbers here, human ideas have an average score of 4.86 on novelty, while AI ideas have an average score of 5.62. And the difference in novelty score is significant, with a 0.03 p-value there. And across most metrics, including novelty, excitement, expected effectiveness, and overall, you see this trend where AI ideas are scoring higher than the human ideas, except the feasibility score. So really, this is a pretty clear trend where AI ideas tend to be winning in this run. And just to put things together, a recap of what we did in this first study: we have a set of 7 NLP topics. We gathered a human expert to write ideas for us. We have an AI agent write ideas for us, and we did a blind review of all these ideas, where all the reviews are done by human experts. And the high-level conclusion we saw is AI ideas have significantly higher novelty score and generally higher excitement, effectiveness, and overall score. So this is what happens when you evaluate these research ideas just by looking at the ideas themselves and compare AI versus humans. I think the natural question to us is, what if you actually execute these ideas into products? Do AI products still win against human products? Well, it's actually hard to say, because I'm sure we all have cases where some ideas that sound super exciting turn out to be totally useless when executed into a product. So it seems like executing ideas into products is a whole different game, and we don't have any guarantee on whether AI ideas will still be winning after execution. So let's try this out. Remember, we already have a bunch of ideas from humans and AI, and human ideas are collected from human experts, and AI ideas are generated by this agent. Now, what I'm gonna do in the next study is I'll just give all these ideas to a set of human experts to execute. Now, some of you might ask, why do we want human experts to execute these ideas? Why don't we just use our agents to execute them? Well, we really thought about this question, and the unfortunate answer is, at least until this point, even the best frontier models are pretty bad at this task of executing research ideas into actual products. Here I'm quoting results from 2 pretty recent benchmarks. First one is paper bench, second one is research code bench, where the task is basically to implement a given research idea into the code base. And you can see that a wide range of frontier models are scoring somewhere between 20 to 30% success rate on these benchmarks. So really, agencies these are not quite reliable on this automatic execution task yet. But hopefully in a few years, they'll be ready for this. But before that, let's just recruit a bunch of human experts to help us execute all the human and AI ideas into the actual products. And here I'm again showing you some of the profiles of the human executors that we have recruited. On the left side, I'm showing you this is a distribution of topics that they have selected to execute. And we have a total of 19 people executing human ideas and a total of 24 people executing AI ideas. And they have an average of 15 and 14 numbers on the Google Scholar profile when they did the study, showing that these people really know this topic pretty well. And they're spending an average of over 100 hours on the execution task. And they come from all these amazing places shown on the right side. So these amazing people will help us execute all these human and AI ideas in your products so that we can compare the actual executed research outcomes. Just some ground rules for the execution study. First of all, we'll do random idea assignment. So for all the research executors, they will tell us their preferred topic, and then we'll randomly assign an idea under the given topic. This is to avoid them self-selecting ideas that they think is actually better, to remove any such self-selection confounders. The second rule is we actually don't allow substantial changes to the original assigned ideas, because the goal of this execution study is really to compare the quality of the ideas generated by AI and humans on its own. So we don't want the executors to add additional ideas to the original assigned ideas. After people spend over 100 hours executing all the ideas, they will submit their full code base and write out their experiments as a short paper and submit us for a round of blind review. And this is pretty much what you expect from a typical conference submission. Here I'm showing you 2 random examples of human projects and AI projects. Remember, these human executors did all the execution work. The only difference is some of the ideas are coming from the AI agent, some of the ideas are coming from human experts. We use the same ACL format for all the paper write-ups. So executors will submit these anonymous submissions to us, and we'll do a blind review on these submissions. So very much like a mini conference. I'm not monitoring your chat, and you can let me know if people are asking any questions there.
Yeah, feel free to continue. I think we can probably stop for a few questions at the midway point, and then after you're done.
Cool, sounds good. Right, so after we have executed all these ideas in your products, we'll give these products to a set of human experts to blind review again. Once again, I'm showing you the profiles of the 58 expert reviewers we have recruited to review all these paper submissions. They come from a bunch of different great places. They have an average of close to 600 citations. So very familiar with the topic, and they're spending an average of 15 minutes on each review. So substantial effort into the review task as well. And next, I'll review the actual review scores when they review the actual projects rather than just the ideas themselves. First of all, I'll show you a bunch of control metrics. So here I'm at the bottom, I'm showing you 2 metrics called faithfulness and code-based quality. Faithfulness basically means we ask reviewers how faithful is the implementation to the original given idea. This is on the scale of 1 to 10. So both human ideas and AI ideas have a reasonably high faithfulness, indicating that the implementation is not deviating too much from the original idea. And second of all, we ask reviewers to look at the submission code base and decide how good the code base is on a scale of 1 to 5. Again, both human ideas and AI ideas have reasonably high code base quality there, indicating the executors are actually doing a good job in the execution. All right. So next I will show you the breakdown on each of the main evaluation metrics in the first block on this table. First of all, on novelty. Human ideas are scoring an average of 4.93 versus AI ideas of 4.73. So here you can see human projects tend to score higher. Next, on excitement, human ideas are getting 4.52 versus AI ideas of 2.90. Again, human ideas tend to be higher. Next on effectiveness, human ideas are scoring 4.84 versus AI ideas of 4.12. Similar trend here. Again, soundness, human ideas are getting 5.38 versus AI ideas of 4.73. And lastly, the overall score, humans are getting 4.00 versus AI ideas are getting 3.40. So it seems to be a pretty clear trend that human ideas are actually getting higher scores than AI ideas across all these main evaluation metrics. And here I'm showing you a slightly different way of computing the scores, where I'm treating each project as an independent data point rather than treating each review as an independent data point. So the sample size will be smaller here. That's why you see a bigger p-values here. But really, the overall trend is exactly the same. If you look at all these different metrics, human ideas are getting higher execution scores as compared to AI ideas. And I tried the ideation scores from the first study that I have described on this exact same set of ideas. And here I'm showing you the ideation scores. So if you remember, the conclusion from the first study was that if you only evaluate ideas themselves, AI would actually be better than humans. And that's what you are seeing here in the first block of this table. Across all these 4 different metrics, you can see that AI condition is actually getting higher scores than a human condition if you only compare the ideation score. And it's a clear contrast with the second block of results, where if you look at the execution scores, humans are actually higher than AI on all these 4 metrics. And just to make this more visually straightforward, here I'm showing you the bar plots of contrasting the scores from study 2 versus study 1. Again, study 2 refers to the execution study, where we have executed all the ideas into products and scored all these products, versus study 1, where we only ask people to evaluate all ideas themselves. And the 1 arrows here indicate how much the score has dropped across study 1 versus study 2. And you can see this trend where for human ideas, i.e. the yellow bars, the drop is pretty minimum. Actually, on novelty, excitement, and effectiveness, the human ideas pretty much retain the same score after execution. And this is a clear contrast against the AI ideas, where you can see pretty big drop on all these metrics, including novelty, excitement, effectiveness, and the overall score. And just to show the breakdown numbers on how much the scores have dropped after execution in this table, I'm showing you the drops in terms of comparing the 2 studies here. So you can see for novelty, excitement, and effectiveness, human ideas pretty much retain the same score. This drop is just 0.0 something. On overall score, they have a slight drop of 0.6. But for AI ideas, after execution, their scores are dropping 1.0, 1.7, 1.8, and 1.9 across these different measures. In fact, if you compare how much these ideas have dropped on the review scores, this difference in the drop is actually very significant across all these 4 metrics. So as a recap for study 2, again, we have 7 LP topics. We have gathered human ideas and AI ideas, which is the same set of ideas we have from the first study. So we have review scores on these ideas before execution, and we gave all these ideas to a bunch of human experts to execute. We score these products again, but this time reviewers are looking at the full paper submission rather than just the ideas themselves. And you can see a pretty different trend where AI ideas are actually dropping significantly more than human ideas. And the result of that is that after the execution, human ideas generally have higher novelty, excitement, soundness, effectiveness, and the overall score. So to put the picture together, you can see we pretty much have opposite trends across the 2 studies when we evaluate ideas versus evaluating the executed products. I'm sure many of you are asking, what's causing this ideation execution gap? Well, here I'll show you one possible explanation for what's going on here. In this part, I'm showing you the many different factors that have been mentioned in the reviews of all the execution and ideation study reviewers. So the yellow bars means these factors are mentioned in the reviews from the ideation study. The blue bars means these factors are mentioned in the reviews of the execution study. And you can see that basically across all the factors, execution study just tends to mention much more factors as compared to the ideation study. So one possible explanation for what's going on here is basically in the execution stage, reviewers are really looking for much more possible weakness of these products rather than as compared to the ideation stage. And I'll give you some more concrete examples to ground this explanation here. So here I'm quoting some actual reviews written by our reviewers. So in the top here, I'm showing you reviews from the execution study where reviewers are saying things like, this method doesn't show market improvements over a basic embassy prompting approach. And that's why they gave it a low score. And you can contrast this with a bunch of reviews from the ideation study when people only review the ideas themselves. Reviewers will say things like, if the experiments show significant improvements to blah, 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 I believe it is exciting enough to get published. And that project got a high score there. And second review is similar. The reviewer said, this is pretty hard to predict. Assuming the experiments are successful and zero, it will be a solid paper worthy of acceptance, blah, blah, blah. So you can see that the language here is highly speculative, and really a lot of the high scores from the ideation study are kind of conditioned on some assumption that this idea will actually work out. But when people execute the ideas and the results are actually not effective, this just changed the review score completely. In a similar vein, you can look at some of the reviews that I mentioned in the execution study, where reviewers are saying things like, lacks comparison with previous work, the methods only compared with the simplest baseline, despite well-acknowledged benchmarks. Another reviewer is saying, the experiments should not just be numbers, but also include discussion of why this method actually produced results, provided the method is also very computationally expensive, or it is not using the same metric as other works, blah, blah, blah. And these kind of complaints are never really observed in the ideation stage, because when reviewers are actually shown the full executed paper, they just tend to think of a lot more weaknesses from these studies, where these are just completely overlooked during the ideation stage. So overall, the strategy here is really reviewers are becoming much more strict and considering a holistic possible set of factors in a execution study as compared to only looking at the ideas, where a lot of times the review can be quite speculative. All right, so before I move on to the next one, maybe I can see if there are any questions.
Yeah, of course. Let's start with John, actually. Do you want to ask your questions?
Yeah. Thanks so much for this talk. This is just great. And my question is about the scoring system. So where did it come from? Did you use a standard set of rubrics that people use, for example, in peer review or grant review? And did you use like a Likert scale, or did you have to invent a different subjective scale? Did you anchor that scale? There's a lot of dangers in these social science tools. I wonder if you had some advice from a social scientist. Thanks.
Yeah, so review metrics are largely similar to standard conference reviewing. So these metrics are largely extracted from conference review forms like ACR or NeurIPS. And we added a bunch of our own metrics just as control metrics here, like faithfulness and code-based quality. And for all these metrics, for most metrics, we use a 1 to 10 scale. So reviewers will give a numerical rating there, as well as a free text review there to justify their score. So that's how the reviewing system works.
Cool, thanks.
Yeah, let's go to Amit next, who raised his hand. Sorry. Yeah, could you unmute yourself, Amit?
Yes, thank you so much. Great talk. So I have a naive question. I'm curious about the distributions of these scores. Did you look at the distributions of these scores and comparatively in human, the distribution of the scores in human ideas versus the AI ideas?
Yeah, that's a good question. So from the execution study, if you look at the top 5 products, most products are actually from humans. But in the top 10, there are a few ideas from AI. So in general, majority of the best products tend to be from humans, but it's possible for AI to come up with a few top 10 products as well.
Thanks. Oh yeah, let's keep the questions in the chat. And yeah, let's go. We can do one more question and then move on. So yeah, from Musa. Let's see. All right. Oh yeah, Musa is asking, are all the gathered human and AI ideas openly available?
Yeah, is all the data are in our GitHub repo, including the reviews as well.
Great.
Okay.
Yeah, let's do the rest at the end.
Okay, sounds good. So at this point, I've covered the 2 dimensions on comparing LM versus experts, comparing LM ideas versus human expert ideas, and evaluating the expert projects versus evaluating just the ideas themselves. Now I think it's a good time for us to come back to judges. And well, in the end, I will argue what we ultimately care about is the outcomes of the executed projects. So the question I will focus on here is, can LMs actually forecast whether an idea can be effective after execution? And the crux here is I want to see whether LMs can directly do the forecasting without going through all the execution stage. So let's see how we can formulate this problem. Now, apart from naively prompting the model, I want to figure out whether it's possible for us to leverage some existing data for training some of these LLMs to do this forecasting task. Well, intuitively, there are actually a bunch of such data, because for every single empirical paper you can find online, they will have such result tables where they will compare the proposed method against a bunch of baselines on a bunch of different benchmarks. So you can kind of extract a bunch of empirical outcomes from all these papers. And I'll just standardize the task format a little bit. So I'll frame this as a binary classification task. So let's say I have 2 different ideas on jailbreaking LMs. I have idea A and idea B, and they are evaluated on a set of different benchmarks and metrics in the paper. I can extract a score based on the majority vote of these different benchmark members to get whether idea A is better or idea B is better. And so the task is basically, I give you 2 idea descriptions, I give you a set of benchmarks, and I want you to predict whether idea A will be more effective or idea B will be more effective. Now, let's first say what happens if we just naively prompt a bunch of frontier language models on this forecasting task. Here, I'm showing you actually all the numbers here are adding retrieval augmentation by default. And you can see that even if with RAG, most frontier models are performing close to random, where 50% is random there. And this is true even for some of the best reasoning models, like O3 there. And next, I'll show you some fine-tuning experiments. So we actually scraped a bunch of papers from all these conferences shown on the left. They come from many different research domains, and we split them into a training test set. The training set has 6,000 such pairs of different ideas, and the test set is all after cutoff date of all these models, and we actually have a bunch of human annotators to verify the labels as compared to the original results in the tables to make sure that all these automatic extracted labels are correct. So result I'm showing on the right are evaluated on this test set of 1.5K idea pairs. So the task is, again, I'm giving the language model a pair of ideas, and I'm asking which one will be more effective on a set of given benchmarks. And you can see that the shaded lines there are showing you the improvement that I can get after fine-tuning these LMs on the training set of 6K idea pairs from past paper data. And you can see a pretty clear improvement from fine-tuning from the first 2 bars I'm showing on the plot here. So these are evaluated on this set of idea pairs extracted from existing conference papers. Now remember, the end goal I was describing was we want an LM system to be able to forecast whether our new LM-generated research idea or new human brainstorm idea will be effective on completely new unseen ideas. So here I'm showing results of using our fine-tuned model on the set of ideas that I have collected from the previous study. So remember, in the execution study, I have collected a bunch of ideas from both humans and AI. I have human expert execute them. That's how I obtain the ground truth execution outcomes. And here I'm asking this fine-tuned model to directly predict the execution outcomes without going through any of the actual execution stage. So you can see that this task is very difficult. even for human experts. You can see I recruit a bunch of really good human experts to do this task. And these experts have an average of over 1,000 citations. They're really expert on NLP, a bunch of senior PhD students. And even if you ask them to directly predict the actual empirical effectiveness of these new ideas, they are only getting close to random performance here. The expert majority means just a majority vote of experts, and the best, it means I take the best expert out of all the experts annotations that have for each data point there. And even the expert best setting is only getting 60% accuracy as compared to our fine-tuned model, which is getting 64.4 accuracy here. So hopefully this is some evidence that it's possible to fine-tune a model to directly forecast the empirical effectiveness of these new ideas.
Hey, Chenglei,
go ahead.
Let me just inject with a question I think a lot of people have. This is an amazing result. This is in some ways the most like crazy result of what I've heard so far. Can you just very like clearly spell out what the training data looks like and how you made it? How many ideas? How did you ground truth, whether they were success or failure for implementation? Did you actually get people to execute all of them? How many data points? That kind of thing.
Right. So there are two sets of results I have, right? So for this particular plot here I'm showing, I'm evaluating this fine-tuned LLM on the set of ideas that I have people actually execute in the second execution study that I have described earlier, right? Remember that execution study I was talking about earlier, where we have 43 ideas actually executed by experts. I have obtained the empirical effectiveness from the actual execution where people are spending over 100 hours there. That's how I got the branches labels.
So it's just like a few dozen ideas. That's your training data.
No, that's not evaluation data.
That's the evaluation.
Exactly.
How many training examples?
I'll go back to that in the previous slide. But again, those roughly 40 ideas are the evaluation data points for this plot I'm showing here. The training data is extracted from existing papers, and you can see that the training data sample size is 6,000. And the way I extract all the ideas, all the training data is I scrape a bunch of empirical existing papers, and I can have all these result tables from those papers where they would describe their method and tell you whether their method is effective as compared to other existing baselines. That's how I can automatically extract all those ideas.
So smart, really cool.
Right. So this is one actual example of what the training example would look like. So from that previous table I'm showing you, I can extract two ideas. One of this idea will be the proposed method in that paper. Another idea will be the baseline method in that paper. They will have actual evaluation results, a bunch of benchmarks. I can get the actual outcome label from that table, and I can train the model to predict this label. And that's the task format here. All right, so back to where I was. So here I'm showing you this new fine-tuned model can actually get beyond random accuracy on the set of ideas that I actually let human experts execute without actually going through the execution stage. So that is some hope that we can maybe directly approximate the execution outcomes without going through the painful execution stage. And some of you might be worried that what if the language model is just extracting some spurious features for making this prediction? Here, we're showing a bunch of robustness checks where we check whether language models are exploiting features like whether ideas published later versus earlier, are models just preferring longer ideas for the shorter ideas, and what if we inject some famous names into the ideas? Would models be biased towards certain things? And across a bunch of different spurious features we can think of, the model is pretty robust, and you can show that, for example, in the first plot here, I'm showing you I'm splitting the idea set into a newer set versus the older set, and model is getting similar accuracy on both sets. Same thing for idea length and famous lab names as a spurious feature. So this is showing you the fine-tuned model is reasonably robust against a bunch of spurious features we can think of. So hopefully this meaning the model is doing some meaningful reasoning to derive the labels rather than just exploiting some surface cues. So as a recap, in the third study, I'm showing you directly forecasting the effectiveness of ideas is a very difficult task. Even human experts are getting roughly random accuracy on this task. But fine-tuned LLM can be better than random and even better than human expert on this task actually. But still, the accuracy is about 65% on this, and this is still far from perfect. But hopefully, this is a starting point for visual people to build on and push for better evaluation or reward models for this task. All right. So
let's try to wrap up in
go
the
ahead.
next 5 minutes so we can have questions.
Yes, that's exactly my plan.
Great.
All right. So going back to the big picture, this is the outline I gave you in the beginning of the talk. Hopefully at this point I've covered some insights on every single dimension here, and hopefully I've answered all these 3 questions on whether LLMs are better than humans on idea generation and how this different evaluation methods differ. I'll spend just one slide talking about some of the existing directions that we're actively thinking about, right? So one direction is how do we train language models to generate even better ideas. The first 2 evaluation studies I've shown you is really evaluating a particular language model on this idea generation task. I'm sure there are ways that we can train these language models to be even better than the results we have got from those evaluation studies. Some possible methods we could try is how do we teach them to iteratively improve their ideas rather than just generate ideas in one shot. How do we inject some notion of research taste into these language models? Another direction we are actually thinking about is how do we build more reliable execution agents so that we have the whole end-to-end pipeline without having humans in the loop to go through the expensive execution stage. And all this work, all the results in this talk are covered in these 3 different papers. The first 2 are collaborated with my advisors, Ta-Sun Lee, and last one is led by Jiaxing, who's a very talented master student when he did the work, and he's going to Berkeley for his PhD in the fall. And you can click the links to read the original papers. And I will end the talk here. We can go through any other questions and have more open discussions.
Awesome. Thanks, Chenglei. Great talk.